Greetings again, this is Scott, known as Cantaloupe to some online, continuing the series of how to create the Platonic Solids via the HTML5 Canvas API. This is going to cover building a dodecahedron, and I'm going to get right down to it. So in this video, the challenge is figuring out how to measure the internal angles of this shape so that all of the sides fit together. This is kind of a unique Platonic solid. It's made up of pentagons, which are obviously 5 sides, versus previously everything has been 3 sides except for the cube, which is 4 sides per face. So this one has other unique properties in that you can't evenly divide it, or symmetrically I should say, and copy that half to the other half without splitting up any of the faces. The octahedron, for example, has a top and a bottom which are mirrors of each other. This one does not. So it's a bit more challenging. It's arguably one of the more difficult ones to create or construct. So what I'm doing with the code is setting up to take a measurement. Now, this is one way to build the shape. It's not the only way. If you look it up online, you'll find a number of tutorials, maybe perhaps other videos that tell you how to make a dodecahedron a whole bunch of different ways. There's ones that involve the golden ratio. There's ones, I'm using my own method here, and it's going to be obvious what's happening here in just a moment. I start with the pentagon, and then I duplicate it. So I have 2, and it's all about the spacing, kind of. It's taking your measurements and being able to move the faces where you need them so that you can put them back together in a way that fits properly. So in this video, that you might notice that the coding, the typing is sped up. That's to spare you from having to watch the whole process, because this one took a little bit longer. This one took about an hour for me from scratch, and I didn't have to necessarily do a lot of research while I was doing that, but there's some troubleshooting involved, so it's played faster than usual. And you see on the screen there's now 2 pentagons, and one of them is bent at an angle, and you'll see as the animation moves forward, or the construction process moves forward, that angle is going to be extremely important. It can't be off, or else the finished shape won't fit together. So I'm starting with only 2 faces, and that's really all you need to actually build the whole shape, and you'll see here in just a moment. I'm going to kind of build a scaffolding is a good way to describe it. It's sometimes when you're building a geometry, when I'm building a geometry, I build a temporary scaffolding. It's something that you would put around a building that you're working on, or in this case, the shape. It's got, you see now there's some numbers marking each vertex, and those numbers in this case are the indices for the loops. So you've seen in previous videos I've had iterators named I or J. That's the exact same thing I'm doing here. I have 2 polygons, so there's a main loop and then a nested loop, and that's what these indices are. There's one number and then a comma and then the other number. So I can tell just by visually looking at the output which vertex is associated with which pair. And this is important because what I want to do is I want to take a measurement between a vertex on the left side and a vertex on the right side polygon. And that's so that I can get the angle correct. I'm going to make micro adjustments to the angle and look at the output. And in just a moment, I'm going to see there's a red line now that shows which 2 vertices I'm measuring between. And the distance between those 2 needs to be the exact same distance as between every two odd vertices of a single face. And that's just a property that we can intuit from any Platonic solid. We know that the points are equidistant from their neighbors and from the center. So I know the next face is going to have to fill this gap here between these two facets, and the distance between these two has to be identical to one of the existing faces. Hopefully that makes sense. So what I'm going to be doing here is like I said, making micro adjustments to the angle. And it's kind of a backwards way to do it, but you can actually dial it in to whatever precision you desire. You can dial it into, and in this case, what I do here in just a minute is I dial this angle in to a precision of about, I want to say 6 or 7 decimal places, which is beyond visual. I mean, it's way smaller than a single pixel at the resolution we're at, so we're good if it's just for graphics purposes. And I just keep adjusting it, and I try to get close. The difference, you see there's 3 lines at the top of the output there, and what I'm looking at primarily is the difference. I want the difference to equal 0, or as close to 0 as possible. And you see I'm getting real close. It's 0.0000. And in just a moment, it pops out into scientific notation, which means the number is so small, the browser doesn't even want to display it as a normal decimal number. It wants to display it as a scientific number. Say that E minus 7 at the end. It's saying this is a very small number. It has a value, but it's not going to be displayed well with a bunch of zeros. So it does that. And there's a way to display it with zeros, but I don't need to. It's close enough at this point. So I have found the number, and I copy it, I take it, and I plug it in as a magic number into this function. I'm going to need that number. And then I just delete the scaffolding. So all this text, the line, the temporarily these polygons are being drawn in the function itself, but that's not going to be happening when it's finished. Of course, I have another function. The normal draw function will be used. So all that scaffolding gets deleted. It was just to get this number. And now, once I have it, the next step is to kind of reposition, reorient this pair of polygons so that I can duplicate them in a way and rotate them in a way that completes the shape, right? At this point, it's pretty trivial. Once I find that angle, it's game over. I mean, you just put them all together, get the spacing right, which might be a challenge, and it's a little bit of a challenge, but what's interesting about regular polyhedra is there's a whole bunch of, not symmetry necessarily, but things that are factors of other things. So once I find the angle, it's not uncommon to find something that's a multiple of that angle, or a multiple of something else that makes sense, like a square root of a normal number, or you just try a couple of different things. Sometimes it's about probing until you find the right number, and it becomes very obvious if you find the right number, because suddenly, click, it's seamless. And sometimes it's close, and you want to make sure you're not making a mistake, especially if it's for something super important. But it's easy to double check to see if you're precise and accurate. So here I have kind of a first attempt at putting it together, and it's not quite right. The top half that doesn't look like the other half of the dodecahedron. And I realized what I need to do is flatten this thing, or at least flatten one of the faces, and then start to build with a flat face on the bottom of the shape instead of like a V shape, how it is now. So now it's flat, one side's flat, and it needs to be completely centered. And then all that's left really at that point is to take the piece that's kind of sticking up at an angle, copy it, and rotate it around. I mean, we know how to do that. Just make a copy, rotate by 2 pi divided by 5 and then iterate, right? So 2 pi is a full circle. We know that a circle, the circumference of a circle is 2 pi over r. 2 pi r, excuse me, not over. So you can, getting into angles is almost a whole separate video, but what I do is I just duplicate it. And what I end up with after that is half of the dodecahedron. And it's not half as in a mirror that you can cut in half, because there's points that go up above where that mirror would be, and there's points that go down below where that mirror would be, and you'll see that in just a moment. Right here I'm centering the object. It has to be centered, or else I can't easily rotate that extra piece. So there's quite a bit of work in this one, but the finished result is a darn near perfect dodecahedron, precise out to 7 decimal places. And if it needed to be more, it's real easy to do that. But for any kind of graphics and even engineering, 7 decimal places is pretty dang accurate if you needed something super accurate. But just about to duplicate those pieces here, and it will be obvious when that happens. Okay, so they kind of fanned out the wrong way, and I'm gonna okay, so there's half of it. The base is complete, and there's the top half, but it's not fitting on right. So the next thing is just to get it to fit on correctly. Now all that's left at this point, you can see there's basically a dodecahedron, but the top half and the lower half, the spacing is a little bit off. And I just took a wild shot at a number that looked like it would work, and it got it super close, and it looks almost complete, but upon closer inspection, like for engineering purposes, you'd want to double check all your numbers and make sure that your shot in the dark wasn't just close, it was the answer, the one that you need. So I checked it, and I noticed that I just got lucky. I happened to get lucky this time with a magic number. And if I zoom in real close, you can see there's still a tiny, tiny little gap there, which means I don't have the answer yet. So what I end up doing is just a little bit more measuring and sticking them together, and then it's seamless. So the final result is a finished, seamless, precise dodecahedron, and that's what you're after. So, and all this work, remember, this is for a function that can be copied and pasted. It's modular is the word. It can be reused. Software design is all about reusing code. You don't want to write something 20 times if you can write it once without sacrificing anything. And now I'm just checking the size, because at the end of this I'm going to want all the shapes to be roughly the same size for display purposes. So that's it. That's the right color, it's the right size, and that's your dodecahedron. The next one is the most fun, and I look forward to the icosahedron. I hope you join me for that video. Have a great day.